So I'd like to do a number of examples of solving differential equations using series. Here's my second example. Let's solve the differential equation y double prime minus xy equals 0. This is a differential equation that you probably can't solve without using series solutions. For example, Laplace transforms are not the best tool here because both x and y are functions of x, non-constant coefficients on y and its derivatives. So the technique is you begin by assuming that y has a series expression, so the sum going from 0 to infinity of some constants a n x to the n. And the goal is to find what these constants are, because if I know what the actual numerical value of these constants are, then I'll know the value of the function y. I'm going to plug this into my differential equation. This is step 1 in my 4-step process outlined in the previous video. In doing so, I'm going to need to take two derivatives. So I'll take one derivative and get the sum going from 0 to infinity of a n times n x to the n minus 1. And the second derivative is equal to the sum n going from 0 to infinity a n n minus 1 x to the n minus 2. Okay, step 2, I'm actually going to plug in my function into the differential equation. So I have the second derivative here, so the sum going from 0 to infinity of a n minus 1 x to the n minus 2. And I'm going to subtract off x times the first derivative, so x times the sum going from 0 to infinity of a n x to the n. And all of that should equal 0. Now in the next step, in step 3 of my 4-step process, I'm going to compare the coefficients of x to the n on both sides. Because of that, I want the coefficients of x to all be the same. So like here I have x to the n plus 2. And here I have really an x to the n plus 1. I'd like them all to match. So I'm going to shift how I represent the two series just so that all the powers of x are the same. What I mean by that is this is really the sum going from 0 to infinity of a n plus 2 n plus 2 times n plus 1 x to the n power. I shifted how I wrote down the series, but did not change the series itself. You could check that both these two series are the same by actually plugging in values of n and seeing that they actually match. So for instance, if n is 0, then the first term is 0. If n is 1, then this first term is 1. If n is 2, then I get a non-zero term. So if n is 2, I get a2 times 1 times x to the 0 power. And you can see that matches if I plug in n equals 0 into this equation here. If you plug in n equals 0, you get a2, 2 times 1, x to the 0. So I shifted things, but still have the same series. And I'm going to do the same thing here. Actually, I'm going to write this as minus the sum n going from 1 to infinity of a n minus 1 x to the n. What happened here? Well, you could see that I have an x in front. That'll combine with this x to have x to the n plus 1 power. My objective is to get everything of the form x to the n, not n plus 1, not n minus 2. So I shifted the series. This time, instead of shifting the index up by 2, I shifted it down by 1. You could check that these two series are the same. If I plug in n equals 0 here, I get a0 times x to the first. If I plug in n equals 1 in the second series, I get a0 x to the first. So the sums actually match. So I shifted everything. Okay, that's step 2. Step 3 is now I'm going to compare the coefficients of x to the n on both sides to get an equation. So I compare the coefficients of x to the n. Now, this time, this first equation is valid for n equals 0. And this second equation starts kicking in at n equals 1. So I'm going to break this into two pieces. If n is equal to 0, I get a2 times 2 times 1 x to the 0. Excuse me, that's the coefficient of x to the 0. This should equal 0. So what I just wrote down was what happened when I looked at the coefficient of x to the 0. This term has a coefficient of x to the 0, whereas this one does not. However, so that was the case when I compare the coefficient of x to the 0 term. When I do x to the first term and beyond, both series are valid. So I get an plus 2 times n plus 2, n plus 1. That's the coefficient of x to the n in the first sum. And the coefficient of x to the n in the second sum is minus an minus 1. And all of that should equal 0. That's when I look at x to the n power for n bigger than or equal to 1. This information allows me to write down a table of values. So let's do that. So here is a table I'm going to write down. I have different values of n. And if I rewrite this equation here, I can write it as an plus 2 is equal to an minus 1 over n plus 2, n plus 1. So I have different values of n in the table. This equation starts being valid at n equals 1. So I'm going to start with n equals 1 in my table. Then I'm going to put 2, 3, 4, and 5, and so on. I'm going to list the values given by this relationship in the second column of my table. So an plus 2, that should be equal to an minus 1 over n plus 2, n plus 1. So let's see what happens. When n is equal to 1, I get a3 here equals a0 over 3 times 2. When n is equal to 2, I get a4 is equal to a1 over 4 times 3. If I have a 3 here, so I have a5 would be equal to a2 over 5 times 4. Now, that's when I get to use this information. This information says that a2 has to be equal to 0. I have an a2 here, so I get 0. Let's do a4. N equals 4. N equals 4 gives me a6. So a6 is equal to a2. Oh, n is 4, so a4. Oh, no, a3. So n is 4, so 4 minus 1 is 3. a3 over 6 times 5. And a3 I already knew from the first row of the table. So this is really a0 over 6 times 5 times 3 times 2. Let's do another row. So I get a7 is equal to a4 over 7 times 6. And a4 I already found in row 2 of my table. So this ends up being a1 times 7 times 6 times 4 times 3. And you can keep going here. I think I'm going to stop doing the table and move on to the last step. I'm going to write down my final answer. So y, it's a series. My series is a0 plus a1x plus a2x squared plus a3x to the third plus a4x to the fourth plus a5x to the fifth. Let's do a6x to the sixth and a7x to the seven and so on. I don't have information about a0. I'm just going to leave it as a0. That will be one constant in my coefficients. That'll be one constant that I get when I write down my general solution to my differential equation. I don't know a1 either, but I did find out that a2 is equal to 0, so that term is gone. a3 is equal to a0 over 3 times 2. So that's my coefficient of x to the third. a4 is a1 over 4 times 3 x to the fourth. a5 is 0. a6 is a0 over 6 times 5 times 3 times 2 x to the sixth. And then a7, last one I'll write down here, is a1 over 7, 6, 4, 3. There are more terms. That is the final answer. However, I like to write it as a constant times one solution plus a constant times another. So I'm going to factor out the a0 term and group all the a0s together. So this is 1 plus x to the third over 3 times 2 plus x to the sixth over 6 times 5 times 3 times 2. And there are more terms. And I'll group my a1 terms together. I think I have an x here. I have an x to the fourth divided by 4 times 3. I have an x to the seventh over 7 times 6 times 4 times 3. And this goes on forever. Here are my two linearly independent solutions to my second order differential equation. And you can't really simplify this. The answer is a series, which is a perfectly valid answer. The answer is whatever function this series is. The series doesn't have a special name necessarily, but this is the final answer. Okay, we'll do some more examples in future videos. Follow me along there.